So let's just talk about linear transformations. So, so we start with a 2D coordinate graph, and we're going to transform this graph. So how do we do so? Let's just say I started with the origin, and then I have a vector. This vector obviously lands at 4, 3, right? It goes 4 units to the right and 3 units off. Okay, we have another vector, and it lands at -4, 1. It's obvious. It goes 4 units to the left and then 1 unit up. And let's just say that this pink vector transferred into the purple vector. So that's transformation. That the pink vector transferred the position so that it is at the purple vector. Just imagine if we transform more pink vectors the same way we did to the original pink vector, which is by moving 8 units to the left and then 2 units down. So just imagine we keep transferring 8 units to the left and 2 units down. Now imagine if I took every single point on the 2D graph. So to understand this, I took every single point on the 2D graph and I'm about to transfer it. So, but however, aren't we transferring vectors? But you can just imagine that we have the origin and all these vectors, all the other points, so each point is the endpoint of a vector that starts from the origin. So if you just transfer all these points, like the arrows I drew below, you transfer them like that, you move them 8 units to the left and 2 units down, you end up with all the purple points, right? So essentially, just to illustrate this more clearly, so you can understand this by rotating the entire 2D coordinate graph. Like, it's kind of like you're moving the space so that all the points move from one spot to another. So we have the blue graph, and we're going to try to transform this point. That's the origin. So we're going to try to transform this pink point. 8 units to the left and 2 units down. So we're going to turn it, and we keep a copy of the original grid. We turn it. We still turn it. We keep turning it. We keep turning it. And we make sure we keep turning it, and we also have to stretch it when necessary, so we stretch the grids. Then we end up here. This is 1, 2, 3, 4, 5, 6, 7, 8, 8 units to the left, and 1, 2, 2 units down. Therefore, we've already done our transformation, and essentially, just imagine, so how do we know how we actually transform, right? Like, did we twist or turn? What did we do? Just imagine your basis vector is shifting, so the basis vectors in the original coordinate plane are I and j. This is I, this is j, right? So basically 1 unit horizontally and 1 unit vertically. If you transform these vectors, so you need 3 I vectors to get to the original pink point. If you transform these vectors into the green vectors, you still need 3 green vectors to transform to go to the pink point. Therefore, if you just transform the red vectors along with your twists and turns, then you'll end up with the green vectors, and every other point is going to be in place. Okay, so essentially so let's just try another example. So we're gonna look at an example regarding linear transformations. We're gonna also look at this numerically. So let's just say I started off with coordinates. So before the transformation, my vector had coordinates xi, or maybe, okay, x1, and then y1. Then I apply this transformation or function, because transformation is another word for function. I apply this transformation, and then I should get vector x2, y2, right? So, however, as the example also showed, the basis vectors still, so the two vectors over here still need the same basis vectors to, still need the same amount of basis vectors summed up. So, for example, if x1, y1 was, if this was 5, 3, and if it transformed into, I don't know, like negative 10, 6, then essentially the relationship is pretty straightforward, right? Like, okay, negative 10, negative 6, I guess. Okay, so the relationship is pretty straightforward, right? You enlarge the vector by 2, so you stretch it by 2, and then you reflect it across the origin. So that it ends up here. Okay, so essentially, but however, if we draw the coordinate plane and we actually shift the whole coordinate graph like we did in the example, and we just shift the whole coordinate graph, then essentially we still use the same basis vectors. We still use the same basis vectors to make the two vectors. For example, right now I need 1, 2, 3, 4, 5, and then 1, 2, 3 basis vectors to make 5, 3, right? Like this, 5, 3 is going to be equal to 5 times vector I plus 3 times vector j. And so if we transform every single point on the coordinate plane, like that, so we stretch the point by 2 times, and then we reflect it across the origin, then we essentially transform the whole coordinate graph, including the basis vector. So the basis vector will turn from 1, 0 into, so you stretch it 2 times to its size, and then you flip it across the origin. So now it's gonna be negative 2, 0, right? And the other vector is gonna be 0, 1. It transforms into 0, 2. And then it transforms into 0. It transforms into 0, negative 2. So essentially, our two new basis vectors will be negative 2, 0, and 0, negative 2. And essentially, you realize that negative 10, negative 6 is actually made up of 5 times negative 2, 0, right? That's negative 10, 0. And then you add that to 3 times 0, negative 2, which is 0, negative 6. So essentially, after you transfer the basis vectors, so if you transfer the whole coordinate graph into a new graph using linear transformation, and so the origin stays the same, and the lines are still straight and parallel to each other and evenly spaced, then essentially you get that, so your basis vector transformed, and your vectors also transformed on the basis of basis vectors, which is probably why they're called basis vectors, because the other vectors are transformed based on these basis vectors. So if I change my basis vector to like maybe negative 3, 0, negative 3, 0, and 0, negative 2, then this over here would have been negative 15, negative 6, not negative 10, negative 6. So that's just how it works. So how do you use matrices to, so how are matrices associated with this in the first place then? Well, one thing we can do is, so we know that, so we're gonna put the original basis vectors into a matrix. So how do we put them into a matrix? So for the first column, you essentially put 1, 0 into the matrix, and then you put 0, 1. So this is vector I, this is vector j, right? Okay, and then after you transform the new matrix will become like, the new matrix will become negative 2, 0, and also 0, negative 2. So essentially you realize that the first column is I. So the first column is vector I. The second column is vector j. And after you transfer, you do whatever you do. The first column is still vector I, the second column is still vector j. Because only that basis vector transformation actually matters. All the other points transformations are the same, so they are still based on the basis vectors. So we only really care about the basis vector transformations. So we write vector I in the first column, vector j in the second column. I've used colors to separate this so you can see. So, and also the two columns have to be linearly independent. So what do I mean? It means that you cannot have, so this is a vector, right? You can't have 1, 0 being being represented by a scalar times 0, 1. And you can't have 0, 1 represented by having a scalar times 1, 0. The same thing over here. You don't want negative 2, 0 to be represented by any scalar times the other component, 0, negative 2. You don't want 0, negative 2 to be represented by a scalar times negative 2, 0. Because if this happens, if they are linearly dependent, then your transformation is basically you transferred the whole 2